The astute observer might have noticed that when we were doing sorting, we worked with doubles, but when we switched to doing searching, I moved over to ints. Now, you might not have thought much of this, but it turns out there was a real reason for doing this. And that is because certain care must be taken when you are searching for doubles, at least if they are doubles that are calculated values. And we want to make sure that you understand why that is. This actually goes back to something that we saw early on when we were learning about the nature of numbers. We were talking about binary, and we just spent a little bit of time talking about the nature of doubles. One of the things that we showed was that 1 minus 0.9 minus 0.1 is not 0. Okay? Which means that if I take that and I check to see if that's equal to 0, I get a false. It also means that if I ask if 1 minus 0.9 is equal to 0.1, I get a false. But if you were doing a search and you had stored in your array the value 1 minus 0.9, and then you did a search for 0.1, you'd probably expect it to find this value, and it wouldn't. And the reason for this, once again, doubles are not exact. When you convert 0.1 to binary, it's a repeating fraction, much like what 1/3 is when you convert it to decimal. For that reason, we have this tiny amount that's left over, right? E to the minus 17. So this is 10 to the negative 17. If we were to write this out in long form, there would be 16 zeros in front of this 2. So 0.16 zeros and then the 2. It really is a very tiny number. But because it's not 0, these equality checks fail. If you have to be searching for doubles and the doubles are calculated. Now, of course, if they were just stored in there as things other than calculations, and if I say 0.1 equals 0.1, if I had stored 0.1 into my array, this will of course be true. But if I've calculated it, then it might not be. If I want that, it turns out that I need to kind of fudge a little bit. And the way that we do this, let's say we have two doubles. We'll call them A and B. In fact, we'll set A equal to 1.0 minus 0.9 and B equal to 0.1. So we have our two numbers here. And we want to be able to ask, are these the same number, at least to the accuracy that we should expect this to give us? And one question is, well, how accurate should that be? Turns out there is a value that we refer to as epsilon, which is the smallest value that you can add to 1 and get something bigger than 1. We can actually calculate roughly what epsilon is. So if we make a var, we'll call it epsilon and say that it equals 1.0. And then while 1.0 plus epsilon is greater than 1.0, we're going to take epsilon and divide it by 2. Okay? So basically, I start at 1, I'll go to a half, a quarter, etc. and keep going down, and this is going to stop when I get to a value that where when I add it to 1, the value is not bigger than 1, and it will actually be equal to 1. And that value happens to be 1.1 times 10 to the minus 16 for doubles. So that's about the right range for an epsilon. Basically, we can't trust anything, we definitely can't trust anything down at that level. If you're doing lots of calculations, a standard approximation for what you should really trust is the square root of that. And for doubles, that happens to be about 1e minus 8. So if I have two numbers, my a and b, and I want to check to see if they're equal, what I would do is I would subtract them, take the absolute value of that, because I don't know if a is bigger than b or smaller than b, and then check to see if that is less than 1e minus 8. And of course, it is, even though a equals b is false. So this type of check here, if you're going to do searching for doubles and the doubles are calculated values, you cannot check for exact equality. You cannot do this. Instead, you need an expression that's like this, so that you're just checking to see if they're as close as you might expect them to be for calculated values.